Now that we've talked about many of the various types of reactions, redox reactions, neutralization reactions, full ionic equations, net ionic equations, we need to return to a little bit of solution chemistry and talk about some of the quantitative factors. So we'll start just with concentration. So concentration for solutions is simply the amount of solute that's dissolved in a given volume of solution. Now, there's multiple different ways to express this. We'll go through some of those. But the most common is the use of molarity to describe concentration. So molarity is simply the moles of the solute divided by the solution volume in liters. So it has units of moles per liter. We often write molarity as having units of capital M. Those units themselves are comprised of moles per liter. So let's just show an example here. So if we took copper sulfate and we were dissolving it in water, if you weighed out 39.9 grams of copper sulfate and then used the molar mass to convert that to moles, you would find you had 0.250 moles of copper sulfate. If you diluted that up to 100 milliliters with water, then you would have a certain number of moles per a number of milliliters. In this case, not 100 milliliters, actually a 250 milliliter volumetric flask. But then we convert that milliliters to liters. What you would find is that we would express the molarity of the copper sulfate solution, or the concentration in molarity, as being the number of moles divided by that volume. 250 milliliters is 0.250 liters. And we would refer to that solution as being a 1 molar solution of copper sulfate. The molar referring to molarity, and it being understood that that is moles of solute per liter of solution. So let's go through a couple examples here. What is the concentration of potassium chloride in a solution made by dissolving 34.5 grams of KCl in 525 milliliters? Well, what we have to do first is we have to figure out the number of moles of KCl we have, and we have to convert our volume, our solution volume, to liters. So we can first determine the molar mass or molecular weight of KCl, add up the atomic masses, and we get 74.551 grams per mole, and then take the number of grams of KCl, use my molar mass as a conversion factor as we've done before, cancel out grams, and come out with 0.46277 moles of KCl. Now, this certainly does not have the correct number of significant figures if this was our final number. But as I've mentioned before, avoid rounding, avoid assigning a set number of significant figures until you reach the very end of the calculation. At the end of the calculation, you can then go back and fix the number of significant figures in your final answer. But if you do it partway through the process, it introduces a rounding error into the equation. So we have our number of moles of KCl. We take the number of milliliters. We take that volume and convert it to liters. It's a fairly simple conversion here. We just divide it by 1,000. So 525 milliliters becomes 0.525 liters. And my molarity is simply the number of moles divided by the number of liters. And then I round it off to the correct number of significant figures. And I come out with 0.881 molar KCl. So we can express the concentration in terms of the molecular species, as we've done here, or we can express it specifically in terms of the solvated ions. So we can talk about something being a certain concentration in ions, not just the molecular formula. So let's go through an example here. What is the molar concentration of each ion in a 0.100 molar aqueous solution of sodium carbonate? Well, if I look at the equation, sodium carbonate will break up into 2 sodium ions and 1 carbonate ion. So if I have 0.100 molar sodium carbonate as a formula, when I look at the individual ions, I see I get 2 sodium ions for every 1 molecular formula. And so that's 2 moles of sodium plus per 1 mole of sodium carbonate. And I come out with the solution being 0.200 molar in sodium ion. The carbonate ion, on the other hand, we only produce 1 of it per molecular formula. And so I only end up with 0.100 molar in carbonate ions. Now, molarity itself, because it is moles per liter, a number of moles per volume, it is just another conversion factor. I can set that to be an equality. I can say that it's 0.100 moles of carbonate ion in 1 liter, so 0.100 moles of carbonate is equal to 1 liter. And I can use that as a conversion factor. So let's show a few examples here. How many moles of calcium chloride are there in 2.5 liters of a 0.125 molar solution? Well, I'll start with the number that is not a part of a conversion factor, and molarity can serve as a conversion factor. So I'll start with my 2.5 liters. 2.5 liters here, and 0.125 is moles per liter. So I can write it just as a conversion factor. Moles on top, liters on bottom. And since liters is what I want to cancel, I simply multiply through and come out with a certain number of moles of calcium chloride. Additionally, I could find the volume of a 0.250 molar solution of copper sulfate that would be required to provide a certain number of moles, 3 moles of copper sulfate. So I have moles, and molarity is my conversion factor. It's moles per liter. I'll start with moles, and then it's 0.25 molar, or it's 0.25 moles per liter, or 0.25 moles is equal to 1 liter, so that's a conversion factor. I can put liters on top or liters on bottom as I need. In this case, I want liters on top because I want to cancel my moles, so I'll put the 0.25 moles on the bottom so that that cancels, and I come out with then a certain volume in liters. Lastly, how many grams of cesium bromide are required to make 400 milliliters of a 1.50 molar solution? Well, molarity again, moles per liter. So 400 milliliters, I first convert that to liters. Then I use my molarity here to convert that to cancel out the liters and convert this to moles. And then that comes out with a certain number of moles of cesium bromide. Now, I'm asked not for moles, but for grams. So the last part is I need to use my molar mass conversion factor to go from moles to grams. So the molar mass is 212.81 grams of cesium bromide per mole. I arrange that so that I'll cancel my moles and I'm left with grams. And that's how we use concentration in a quantitative fashion.